So let's begin. Good evening, everyone, and welcome to week 11 of this live interaction session for the course of Matlab based programming lab in chemical engineering. Right. So in this course, what we do is we learn about use of Matlab and programming in the Matlab to solve various chemical engineering problems. Right. So we have started with the basics of Matlab in the initial week 1 and week 2 lectures, right, where we learned about the need for the modeling and simulation aspect. Then we worked our way towards understanding the various commands, various basic loops in the MATLAB, and then after that we move forward with solution to different types of problems, be non-linear equation, solution to linear equation, solution to simultaneous system of equations, right? Or we learned about ordinary differential equation and their solutions, partial differential equations we have been looking from last two lectures, right? And then now we are at the end of this course where we will learn about the optimization process and some curve fitting aspect or the data fitting aspect, right? So before I start the contents of today's class, some note from the last lecture, right? So in the previous lecture, what we were doing was we were understanding about partial differential equations and problem uh, related to partial differential equations and how to solve them, right? So we started with what are PDs, how it looks like, the general form of the partial differential equations, how we can categorize partial differential equations, right? So we have either parabolic, hyperbolic, elliptic, depending upon the condition that it satisfies, right? So if I have a second order linear partial differential equation, and if we write it in this particular format where the second order derivatives are assigned the coefficient a, b and c, then based on the value of b square minus 4ac, either you assign them whether the function is parabolic, hyperbolic or elliptical, right? We looked at some of the examples that we come as a that comes as a problem to us, right, in a chemical engineering. So we have heat equations, wave equation, Laplace equation, where your heat equation will behave as a parabolic, Laplace equation behaves as elliptic, and the wave equation as a hyperbolic, right? What are the various boundary conditions to use in this partial differential equation? So we have two types of conditions: one initial condition and one bound. And another is boundary condition. So when we are solving PD, mostly we will need this both conditions. When we are working on the problems of ordinary differential equations, so mainly either we have ordinary differential equations with initial conditions or ordinary differential equations with boundary conditions, right? So these two categories. But when we are working with partial differential equations, mostly we have combination of both, that we have initial condition as well as some boundary conditions associated with the partial differential equations. Now, so solution of the PD requires, if it's a simple problem where if the expression of your partial differential equation is simple, then we can use analytical methods such as separation of variable, method of characterization, or some integral transformation method, right, to solve the partial differential equations. But most of the equations that we come across are more complex than the method that we can use for the analytical part, right? So we rely on the numerical solution, where we learned about finite difference method, finite element method, and finite volume method, right? So finite difference method, we have already worked problem for that from last class. It should be week 9 class, yeah, right? So in the week 9 class, we solved the problem of heat transfer in fin through finite difference method. Then we looked upon finite element method, what is the idea behind finite element method, right? And most of the MATLAB PD solvers, they rely on the finite element method, where your domain is divided into the various grid points, and for each grid points you create multiple equations and then solve it simultaneously. So for Matlab we had this PDP solver, which is used for one-dimensional parabolic equations. And if you have other 2D problems, then you can use PDE tool, which has both GUI based interface as well as the command line interface, right? And then we solved some of the problems, right? Now what happened in the last class was that we were confused about how to store this data. So when we are storing the output from this PDE modeler, what we are getting is that we are getting a unit vector, but our system, let's say, is divided into two dimensions. Then how to differentiate which value corresponds to the which part? So for that, let's look at some example and clarify that how to interpret that data, so that we can plot it further down the road when we required it. And okay, it's not loading. Yeah. It's opening it two times. Just give me a few minutes. It's taking longer than usual. It should work faster. Has anyone joined? Okay, no one. Anyway. So if you recall, let's consider any example from the last class. let's look at this example where we were looking at the cross sectional area of shell and tube heat exchangers, specifically looking at the tube part, where outside you have a hot fluid, inside you have a cold fluid. Then what will be the temperature profile within your cutout of your tube, right, along the cross sectional area. Yes. So this is how our profile looks like. So you can see the outside, which is subjected to hot fluid, has a higher temperature, which was kept around at 70 degrees centigrade, and inside fluid was at 30 degrees centigrade. So this is how temperature will flow from outside to inside, the heat transfer direction, right? And this is how the gradient looks like. Now here what we are interested in is how to store this data. So if you will see, when you click on the solve part, you have a export solution option. In the export solution option, we have variable name for the solution, which by default it gives the only u value. If you press OK, here in your workspace, u variable is created, which you can see it's a vector with some 1800 entries, right? And these are the temperature values. So these are the temperature values, but for us to interpret it, like which value corresponds to which specific point within the circular cutout, we need the coordinate data also, right? Now here you can see, like, we have the value of 70, which is obviously the outside value. Then comes the value of 30, which is actually the inside value, and 52, 51, 60, 43, this will be some intermediate value. So we need to know what is the exact precise location. Yeah, obviously we are getting the graph when we are running it, but then let's say when you want to do some post-processing analysis based on the temperature profile within the cylindrical cutout or any other case that you are considering, right? So in such cases we have to know the position at which temperature, position at which we also have the temperature data, right? So for that, go into the draw part, not draw, yeah, sorry, mesh part. In mesh part, you have an option of export mesh. When you click on that, this terminal will pop up, which shows the variable name for the mesh data. So you have points, edges and triangles, right? So P, E and T, these three variables are there, and when I do OK, it will export these three matrices, vector P, sorry, matrix P, matrix T and matrix U, sorry, E1. Okay, so here P, as it says, it's a point matrix. So here you have 2 rows and 1812 columns, right? So these 2 rows, this number, like the column number of 1812 is matching with your u values. Now here the P, which represents your data point, actually represents the points in your mesh grid part. So again, if I do export mesh, I have point which is represented by P, edges represented by E and triangles represented by T. Okay, so P means my projection points. Okay, so this are the first row is nothing but your x coordinate, the second row is nothing but y coordinate, right? So if you just do a plot, let's do a scatter plot, okay, of P, first row all column, then second row all column, sorry. So this is kind of your mesh point, okay? So all the points values are given, and corresponding to this point value we will have our temperature data. So for first point, where x coordinate value is minus 0.4619, y coordinate is 0.1913, your u value will be 70. For second point, its coordinate is 0 minus 0.5, your u value is 70. Third point, 4 point, similarly, right? So in this scatter plot itself, you can further add the value of your u. If I do help scatter, now here scatter field, yeah. So which part I want to show you is this scatter x, y, s, z, c. So x and y are coordinate, sz provides the circle size for the scatter plot, and then c, you can, so for with the c what you can specify is a circle color. You can specify one color for all circle. So in this case we can consider a c value as a temperature part, right? So we can have a gradient for the temperature to represent our data. So instead of writing, let's say I write scatter xy coordinates, the size you can put, let's say I'm putting as of now 10, and my u vector, which is my temperature vector, and then I plot it. So this is how my plot will look like. So here, according to the value of u, this color of our dots, colors of our circles are decided, right? So the center part has a blue color, which here you can see it's at 30 degrees centigrade, so all has the same value. The outer layer is at 70 degrees centigrade, so they have some same value, and in between the gradient part. We can do it this as a filled part. So for that you have to write it filled. You can do shift enter so that it won't execute a command. I can add a color bar also and do a plot, right? So this is how it will look like. So this is our circular cutout. Inside temperature value 30 is given, outside value is 70, and in between the data points, right? So this way what you can do is you can extract out the data from the Matlab of your output variable. Okay, that output variable will come in the form of the vector. It will be mostly column vector, right? But corresponding to that vector you can also get the mesh grid data points, which will denote that what value at what coordinate you will get the corresponding output value, right? So in this case the p matrix, it represents your xy coordinates, right? Similarly for other case also your p matrix will represent xy coordinate, and corresponding to that xy coordinate, so let's say if I consider the fourth column in the p matrix, right? So that will correspond to the fourth row in the u vector. Okay, so corresponding to the fourth column in my p matrix, my data value will be the row of fourth row of u vector. Okay, so this is how you can interpret your data for the further post processing analysis part. So I had told you that I will show you how to store this data. So this is that part. Now let's move forward with the today's aspect, which is on optimization part. We won't be doing any PD problems today. I think the previous example were sufficient enough for you to start with. You can do various experimentation, some trial and error to understand the PD modeler more on your own. Okay. So the focus of today's class will be on the optimization aspect. What is optimization, why we need the optimization, part what are the inbuilt MATLAB options that we have, and then some short problems on the optimization problem, right? So there is no specific big problem that I'm solving today, but there are chunk of small problems. Let's begin with that. What time it is? Yeah. Okay. So when we say the optimization part, what do we mean by optimization? So optimization in general is like finding a best available option from whatever available data set or alternatives you have, right? So although it's a mathematical term, but we use optimization in our day-to-day life also, right? Which route to use, which will be the shortest path to reach from location A to B. That is something about the optimization, right? So it does not have to be expressed explicitly in terms of the mathematics. It's just general day-to-day life also involves the optimization part, and we as a chemical engineer or any other engineer or in any other field have to come across some decisions, right, where you have multitudes of options, out of which you have to decide which option will best suit for our requirement. For example, what should be the column internals, what should be the column internal specification which gives us the best separation efficiency while being within our budget, right? So that selection part is nothing but the optimization. You cannot always go with the higher efficiency equipment, because as your efficiency will increase, your cost for the equipment might also go high, right? So you have to see and balance out what is your desired output that you can get within your considered budget. So that is the basic part of your economics, right? So in such cases you have to do optimization. So same was the example of this crude oil separation for the week 11 class from source nodes, right, where you were doing optimization to find out what will be your profit for which production rate you will get the maximum profit. Okay, right. So that part, this finding this best option is nothing but a optimization, right? So be it be the maximum or minimum of your objective from available set of option is optimization. Now when we talk about optimization, so there are three important aspects of optimization. One is obviously you have to have some objective function, right? So objective function is nothing but the mathematical form which will represent your desired output or desired throughput, right? So in case of the search example, it was the profit that we want to maximize the profit, right? In some cases you want to minimize the waste of your solvent, you want to minimize the flue gas outlet that is going from your furnace or anything else, right? Minimize the wastage of your catalyst or something. So that could be the objective function can represent anything. Your separation efficiency can also become your objective function, right? So either you minimize it or maximize it. That is your objective function. Then you have variables. So variables are your part of your objective function. So these are the independent variables that you can vary according to which your solution or your objective function will also change, right? Now many a times we come across some constraints. So these constraints constraints are nothing but they limit the value of our variables or objective functions, right? So in case of let's say in case of distillation column, you want to maximize your separation efficiency, but at the same time maintaining some specific requirement of top product and the bottom product, right? So then your mole fraction values of top and bottom products will have to have some fixed quantities, right? They should have some fixed specific requirement to be met. Okay, so then it will come under the constraint part. Now in constraint also you can further divide it into inequality constraint, equality constraint. Now the difference in the equality and inequality constraint will come when you are trying to solve this problem, now the optimization itself, sorry, now field of optimization itself is a much bigger aspect, right? So there are specific courses uh, developed or designed for understanding the optimization part, right? So depending upon what kind of objective function you have, what kind of constraints you have, how many variables you have, you can categorize your optimization into single variable, or univariable, what you call it, uh, or multivariable problem. Then you have linear optimization, non-linear optimization, you have constraint optimization, you have unconstrained optimization. Within the constraint also you have equality constraint, you have inequality constraint, right? So depending upon your type of problem, type of your objective functions, type of your constraint, your optimization problem can be categorized into different parts. Now this different types will have some different solution strategies. Okay, so since this topic itself is much vast, I am not going to the numerical solution aspect of the optimization problem, right? But still we have used some of this optimization aspect previously also. So previously we studied the Newton-Raphson equation, RK equations, right? Where we were trying to solve the f dash x equal to 0, so x value which will lead to the uh, differential value is equal to 0. So in that case, that is nothing but the optimization part, right? So for any value to be optimum, for function to be optimum, its first derivative will be 0, right? So in such cases you have to find the x value which will give the give your differential value of your function to be 0. We used f0 fsolve command previously, right, where we had this non-linear equation and we were equating it to 0. We were finding the value of x through the bisection method, golden section method, and other such solution method. So that is nothing but that is also an optimization process. So this all thing combined comes under the part of the optimization. Okay, so that's why it's a very vast part. So I'm not going into the details of each and every numerical method into that, but rather what we will do, we will just focus on what are the options that we have in Matlab to solve this, to solve various optimization problem. Okay, so I have listed some of the few commands which are available in the Matlab to solve your optimization problem, right? So mainly if you start with, you have seen this first three part probably, fmin unc, fmin con, fmin bnd. Okay, we will go into the description of each of this command. Then you have some fmin search, linear progression, quadratic programming, pattern search, ga method, least square non-linear equation, least square curve fitting. Okay, so there are multiple options already pre-built available in Matlab that we can directly use to solve the optimization problem. So let's say if I just search about the optimization in the document, since I don't know much which command to use where, basic strategy will be to start with the documentation, like understanding the documentation part. So even Matlab has some optimization toolbox also, right? So first thing comes is the optimization toolbox. We won't be discussing toolbox as of now. Right, so here the first part comes that optimization is minimum of single and multivariable function, non-negative least square or root of non-linear functions. So optimization finds the location of a minima of a non-linear objective function, right? So you can use one variable, you can find a minima of a function for one variable on a bound interval through f min b and d, which is bound, or a minimum function of several variable which are unbound through f min search. if you want to find a non-negative solution to a linear least square problem, you can find it through LSQ, which is least square non-negative. Okay. Sorry, non-negative. Yeah, this is non-negative. Then f0, as I said previously, we also used f0. So f0 is nothing but that is also an optimization part where you equate the function to the zero value. So you find the value of x2 which satisfy this. Okay. So there are some description given that fmin bind finds a minimum single variable function of a within the fixed interval. Fmin search finds minimum of unconstrained multivariable function using derivative free method. So this derivative free method is again type of numerical method which is coded behind the fmin search function to solve the problem. We again won't focus on that aspect. F0 uses finds the root of nonlinear function. Then you have this different options. Apart from that, let's see what other things we can find about the optimization here. We have optimset, minimax optimization. This is something new, not this one. Yeah, this focuses on the actually solver part more. Let me search minimum. Bounds fmin search. Fmin search find the minimum of unconstrained multivariable function using derivative free method. There are these examples given. I thought there was this option. So there is multitude of content, but I want to focus on the current functions only. So let's start with the fmin unc function. Help fmin unc part. So here this finds a local minimum of a function of several variables. Okay, where you have to provide the function value and the initial start point, which attempts to find a local minimizer of f or a local minimizer x for your given function. Okay, what else? You can provide the exit flag. This is fine. So this is how you can provide your function. Like you can write fmin. You have to provide the function value and some start point. The option command will give you the some output flags, like for the option part. You can again go into the documentation what extra options you need, which will provide kind of number of iteration it took to solve the problems, in between values that it found for the optimization. Exit flag also can be provided, which will give you the comments on your results, right? How your system has converged or not. So here option, then you have second option is fmin con. Help fmin con. So see the above function, like fmin unc, that was minimization of multivariable function, but here we hadn't specified anything about the constraint. So it's in a way unconstrained optimization, right? You are not providing the constraint part here. But let's say if you have a constraint, then you have to use fmin con, which finds a constraint minimum of a function for a multivariable function. So f min function is again multivariable optimization, but here you also provide the constraint. Now the form that you provide your constraint is very specific, right? So here this is the equation that you have to follow, that you have your inequality constraint, which is ax is less or equal to b, then ax is equal to b, which are linear constraint. Non-linear constraint are given in the form of c, and then bounds on your equation, right? So the way you provide this data is you provide you start f min con, provide the functional value, provide the initial input part, which is x0, then your first comes the linear constraint, that to inequality equality constraint. If you want to further add your bounds, so you can add it as lower bound, upper bound. Let's say you have a non-linear constraint also present. In that case you have to write x0 a equal lower bound, upper bound, the function non-coopset adjoint factor c0. Yeah, so non-equality constraint you have to write in form of this function. You have to add it in the form of a function. So let's look at the example part if they have provided here. Yeah, so here is your function, which is this is our objective function. For the non-linear constraint part, you have to also create a function, non-linear equality and inequality constraint, that see here these options, cx less or equal to 0 and c equivalent c0. So this you have to provide in the form of this two part. So this is inequality constraint, equality constraint, and then you can put it into your function like this. Sorry, yeah, this part, my function, your initial guess. Here they have not considered any linear inequality equality constraint. There are no bounds on your system, okay? So that's why these things are empty. The linear equality and non-equality constraints are empty. There is no bound, so you have to provide just blank blank vector data, and then your non-linear constraint, right? So this one f min function, let's write it down, is a multivariable unconstrained optimization problem, or optimization, yeah, multivariable unconstrained optimization. F min con is multivariable constrained optimization. Here it should be this. Now here the both method are actually the gradient free method, right? It was mentioned in the start. Constrained minimum function of server implements different algorithms. No, this one is not constraint free, sorry, gradient free. Interior point. So see here there are they have mentioned various functions, like various method they use. So you have interior point method, SQP method, active set and trust region method. This again requires a time and concept to explain all these methods. So if you are interested, you can look into the optimization books and understand this these numerical methods. This is also gradient based, sorry, so there is nothing about non-gradient here. Yeah. Okay, now next we have f min bound. F mean PND help. So this is a single variable bounded non-linear functional minimization process, right? So this is for the single variable, and then you have bound on your function x1 and x2. So sorry, this is bound on your single variable, so x1 and x2 are kind of lower and upper limit, my mistake. Now here, this is an unconstrained optimization problem. Sorry, it's in a way constrained, that you are providing the bound on your x value of x, so that in that sense it's a constraint, but apart from that there are no other constraints that you are using, right? So this is like finding an optimum value of your function, or minimum value of function for the univariable part within a given interval. Okay, so this is univariable optimization problem within bounds, within a given bound. Limit. Okay, then you have f mean search. Just give me 2-3 minutes. Okay. sorry. Okay, so here we are with the we looked at the um, uh, three commands, right? One, fmin bound, which is univariable, fmin unconstrained and constrained. Now we have fmin search. Fmin search is multi-dimensional unconstrained non-linear minimization problem. Okay, so again you start the way you can provide is like you provide the function value, you provide the x0 value. Here what further you can add to this is it's multivariable unconstrained nonlinear minimization Nelder-Med problem. So it specifically uses this method. So it's kind of similar to your fmin unconstrained. So it's unconstrained multivariable optimization process, but it is based on the specific method, the Nelder-Med method, right? So here this is again kind of a same part, that this thing is multivariable unconstrained optimization with Nelder-Med simplex method. Okay, or just simplex method. Yeah, simplex method is a well-known popular method of optimization. So this uses a simplex method. Then you have linprog. So if I search help, see there is this f0 command also and fsolve command. These are also kind of a optimization problem solvers, but we don't consider it as a kind of optimization part, but again you can categorize them in the optimization category. Okay, similarly you have fsolve command, which is multivariable part, which equates your function to 0. So what difference you have when you use optimization function and f0 or fsolve command, right? So f0 and fsolve, they try to equate your function to the 0 value and find the corresponding x value which will satisfy your condition, right? And when you are using this fmin constrained or unconstrained problem, what it does is that it finds the minimum value of your function. Okay, now to find the minimum value, as I said, let's say if a function has a minimum value, then its first order derivative should be 0, right? This is the basic concept, that if the function value is maximum or minimum at x star, then the function derivative at x star will equivalent to 0, right? So what you can do, instead of using this fmin constrained or unconstrained optimization solvers, if you have the function derivative form already present, then you can equate it to 0, find the corresponding x value. At this corresponding x value, either your function will be minimum or maximum, and then you can check it, right? By putting it into the function, that whether it's a minimum or maximum. So still it's a part of optimization process, but slightly different, because here we are not specifically saying what function value we will get, whether it's a minima or maxima. But when you are using this f minimum optimization solvers, you are specifically looking for the minima. Okay, so the commands are designed in such way that they will keep a check on the function value variation also. Here also you have this method which are derivative based. So anyway you will find the fx values which will be put into the equations of your solvers, right? There will be checks for fx is equal to 0, or the function value there will be checks on your fx is equal to 0 in this fmin solvers also, right? So you can use this sort of a command also, so that rather than using your function, if you have derivative already present, you can do that. Now next we have linprog, help linprog. So this is linear programming. It attempts to solve the linear programming problem. Minimize f dex x subjected to ax is equal to less or equal to b, right? So it solves the problems above while additionally satisfying the equality constraints. So here you can also provide the a b equality constraint, inequality constraint, lower and upper bound. Always look for some of the examples. So if the examples are not given in the help window itself, you can go into the detailed documentation. Similarly, you have quadprog. As it name says it, it's used for the quadratic programming, right? So it attempts to solve the quadratic programming. So minimize your quadratic function subjected to the some equality and inequality constraint. Okay, so this is specifically designed to solve the linear or quadratic problem, right? Then what next? We have pattern search method, GA method. So help pattern search. No, I wrote a wrong spelling. Okay, it requires some toolbox to install. I haven't added it yet. Help GA. Yeah. GA not found. No. So I think GA is also part of this global optimization tool. Then you have least square curve fitting. Help LSQ curve fit. So here this is as it says, it's a least square curve fitting method. This also you can use for your data fitting. Least squares curve fitting and non-linear equation, and then F goal attained, right? Help F goal attained. So this is, it solves multi-objective goal attained optimization problem, right? So there are various options available. Obviously going through each and every one requires some sort of understanding. So my suggestion will be that you start with a basic optimization options available in the Matlab, and depending upon your problem you move forward with the other higher options that you have, like more customizable option that you can use it, right? So let's start some of the programming part, some of the problem solving, and then see how to use these functions. So first you have problem number 1, which says locate the minimum point of Himelbube function fx, which is given as this. Initial starting point is given as -5 to +5, minus 5 and +5, sorry, for x1 and x2. Using at Matlab function fmean search, use the optim set option to set the optimization option to display all the iterations, and set function tolerance as 10 to the power -8. So first let's solve it normally, and then we will use this optim set option. So here we have been asked to use fmean search. Now what fmean search does is it is again the multivariable unconstrained optimization problem, but it's specifically with the simplex method. Then we will compare this fmean search with fmean unconstrained and try to see what difference we are getting, right? So here we have a function. So let's create a script. Okay, let's say f is equal to @x1 x2, and your function is x1 square plus x2 minus 11, this whole square plus x2 square minus, sorry, plus x1 minus 7, okay, plus x1 minus 7 whole square. So this is our function. Then x0 value is given as minus 5 comma 5. Now let me use it calling fmean search option to solve this problem. So my solution, let's call it as solve, is equal to fmean search. You have to provide your function, you have to provide your x0 value. Let's run it and see what happens. We got some error. What it is? Incorrect dimension for raising a matrix to a power. x1 x2 let me add this dot star here. And then just a minute, why this error is coming? It should not be there. This has created perfectly. Not enough input arguments. Just let me quickly do fmean search help. Yeah, here. So we have provided the function. Oh, the way I'm calling the function is giving you an error. Let's look at some example. So this is the function, yeah. X value is given, so f means search function and x0. We have done the same thing. X1, 2. Okay, got it. The error is I was giving it a 2 variable part, but it's a 1 variable and part of it is an answer. So here, yeah. So now it should work. So initially I was providing x1 and x2, but it was considering 2 variable. But obviously we can provide x as a vector which contains x1 and x2 component, and now when we call it, it should solve it. It has solved the function and given the value. Right now, let's find the value of our function at these two particular points, which is @f minus 2.8051 comma 3.1313. So this is close to 0, obviously. So this is your optimized value. Now in the fmin search, what have been asked to us is use optim set option to display all iterations and set function tolerance as 10 to the power minus 8. So let's say in the option part, what extra things we can provide. So here is the option. Yeah. So we can provide options as optim set and all the corresponding values. Let's do that here. Options is equal to optim set what things we want to provide. We have been asked to provide display output of each iteration, like option to display all the iteration, right? So if I do the display, it will display all the parts, right? So let's select display. Here, display, its value should be that we want to see all the iterations. So I'm writing iter. After that, what have been asked to us? And set the function tolerance as 10 to the power minus 8. So for the tolerance part, tol function, terminate tolerance on the function value a positive scalar. Default is 10 to the power minus 4, but we want to set it to 10 to the power minus 8, right? So tol func it's tol fun, capital F, and the variable is e to the power minus 8. Now again, when I do solve, is equal to f mean search, this time f x0 and options. and let's run it. Opting set display is unrecognized. Why? This. Okay, yeah, got it. I'm providing it wrong. Display also should be in the inverted comma. Tolerance value, tol function will be also, and this will represent like this. Yeah. So this is how we are getting the iteration value. So iteration, function count, minimum function value, and what procedure they are doing within this function, right? And at the end, this is our value. So almost values are same, but if I now find the function for my solution, this value goes to 10 to the power minus 9 because our tolerance was increased. Previously it was 10 to the power minus 8, right? Then another thing we wanted to compare was the result. So the result is here, minus 2.8 and 3.13. Why it's not here? X. Let me check. X1 square plus x2 minus 11 square, x2 square plus x1 minus 7 whole square, minus 5. Oh, I don't remember this option part here, but this is I think correct part. Minus, oh, both are minus 5. What options I have given? Yeah, sorry. If I take both minus 5, then I'm close to this value, 3.779, so 78 and 3.28. So for optimization, initial guess will also give you a different result, right? So the function value at this particular point is also 10 to the power minus 9. So it's a this function has a multiple local minimas, out of which the closest to the initial guess point value is provided to us. Now we wanted to compare this, since f mean search and f mean unconstrained both are similar. What should be what kind of value we will get? So let's try and check it. F mean unconstrained, you need a function, you need the x0 value, right? So let me change then the name, solve by search method and the solve by unconstrained method. We will display Let's see. So for the both case, we are getting same values, minus 3.7793, 3.2832. But if you will see the search method, it took 42 iterations and then gave us the answer, while the unconstrained f mean uncon did the solution within the 9 iteration. Now the number of time the function evaluation was happened, so for this it was 81 times, while for this only 30 times. Okay, right? So you can see the difference between the two methods by looking at what are the options that you are getting. Here your accuracy is also even more, 10 to the power minus 13, compared to here where your accuracy is 10 to the power minus 9, right? So this is the difference. You are getting the same solution, but depending upon what kind of optimization method, what kind of numerical method is being coded within that particular command, you will get a slight difference in the value or difference in the accuracy, and the speed will also be different. Again, the kind of problems that we are doing here are much simpler, so there is not much difference when I use f mean search or f mean unconstrained part. But if you have a much bigger problem, these problems which requires multiple iteration, much higher accuracies, then selection between such method is an important aspect that you have to pay attention to it. So for that, obviously you have to read more and understand about what kind of problem you have and which specific method will suit more to your problem. Okay, so that was that. Now let's move forward with the next problem. I think this has a So problem number 2 is use f mean unconstrained Matlab function to determine the minimum value for this function, starting with this given data points. So now my function will change, f will become iterate x. My function is e to the power x1 into 4 times x1 square two times x2 square four times x1 into x2 plus 2 times x2 plus 1. Four times x1 x2 2 times x2 plus 1. I'm using solve is equal to f mean unconstrained my function and x0 value. Okay, my x0 here is given as minus 1 and 1, and then display function value at optimum point is display my f solve, and let's run it. Right, function value at the optimum point is 10 to the power minus 15, which is close to 0. So option C is your answer. Now here local minima should not comment this. Yes. So this is my optimum point minus 0.5 and 1, and corresponding to that I am getting the value of 0. Next we have another example of F mean search. Just give me a few minutes again. Sorry for that. I will be back in 2 minutes. So we have a f mean search problem. We have been given a function and we have to minimize this function with the starting point given as 0 0. Now by the way, here I have just provided mean search. You can use f mean unconstrained part also, or even the constraint part also, where you don't provide any constraint, so you keep all the other variables as 0 0 blank matrix. Okay, then also you will get the same sort of a value. So here let's code this. This was my problem 1. Now we have problem 2, end of it, and problem number 3. Okay, so now our function becomes four times x1 square 3x2 square minus 4x1 x2. So like again the same equation here. I will just copy paste it from this point. For x1 square 3 times x2 square minus 4 times x1 x2 minus 4 times x1 x2 plus x1. Okay, plus x1. So this is our equation. X0 value is given as 0 comma 0, right? Yes. Then solution to this will be f mean search function value x0 value. You can here also use an exit flag command. I think that is this might have a syntax error, but anyway, let's see. You can use exit flag command to see how your optimization has converged. So we have to determine the minimum value, right? So again, let's run this. Help f mean search. Okay, sorry, exit flag will come on the left hand side part. So here, instead of just solution, I can provide solution f function value at a solution, then exit flag here. Yeah, you can just directly write f solve. So with the starting point as 0 0, your optimum value comes at minus 0.187 and minus 0.125. Your function value is 0.0939. Exit flag is 1. So what does this exit flag mean is maximum coordinate function difference between the current best point and the other best point in the simplex is less than or equal to tolerance, and corresponding difference in function value is less than or equal to tolerance function. Possible exit flag maximum of. Yeah. So this shows that we have reached our tolerance criteria. Okay, that's why we are getting the flag as 1, which is says that okay, you have reached your criteria and this is your function values, right? So what should be the corresponding answer to this is, my value is here, sorry, yeah, minus 0.0937. so it's the closest option, so minus 0.1, that is your answer. Now next we have consider the following optimization problem. So we have to minimize this function 100 times x2 minus x1 square plus 1 minus x1 square subject to constraints. So we have one inequality constraint, one equality constraint, and two bounds on your function, right? So obviously this is a constraint optimization, and for constraint optimization we will use fmin_con command, so which is multivariable constraint optimization part. Here what else we have to do, we have to provide an initial guess that has been given. Okay, so let's try to solve this part. How much time we have left? We have still, I think, 20-25 minutes. Yeah, okay. My function is 100 times x2 minus x1 square minus x1 square, this whole square, plus 1 minus x1 square, 1 minus x comma 1, this whole square. Right. Okay, so this is one thing done. X0 value is given as 1 1 1 comma 1. Now we have to use fmean constraint part, right? So here we have to provide the equality and inequality constraint. So for your linear constraint, what kind of constraint we have? Let's look at them first. So this both constraints are linear. So for linear constraint, I have to provide the two matrices A, AB, and A equality constraint, AB equality constraint matrix. If I have a non-equality constraint, then I have to create a separate function to represent non-linear constraints also. Sorry, not non-equality, but if we have a non-linear constraints, for that we have to create a separate function. But for the linear equality and non-equality constraint, we have to provide the coefficients value, right? So here the coefficient value, this is how we will write the function. That function initial guess A and B value, which is for the inequality constraint, A equivalent, B equivalent value for the equality constraint, lower and upper bound for the x values, right? So let's see how to provide this. So I have to provide the first A value. Now A value here will be the coefficient of x1 and x2 for inequality constraint. So that is 1 and 2. 1 comma 2. I can uncomment this. Then B value. B matrix is my right hand side value, which is 4. Again here the sign is important. So the format that we have to follow is that Ax is less or equal to B. So if you had a constraint which had said that x1 plus 2 times x2 is greater or equal to 4, then you have to reverse it so that your so that you get less or equal to part. So your right hand side will become minus 4. Okay, so this is an important thing to keep it in mind, right, when you are solving it. Now 2 times x1 plus x2. For the equality constraint, I have AEQ is equal to 2 comma 1, BEQ is given as 1, then lower bound. So for the lower bound of x1 and x2, it's 0, 0 comma 0. The upper bound is given as 0.4. Now our solution is equal to f mean constraint. We have to provide the function value, x0 value, a value, b value, AEQ, b equivalent value, lower bound, upper bound. Okay. Now let's see, run this. So you can see it has provided the message that optimization completed because function was non-decreasing in the feasible direction to within the value of optimality tolerance, and constraints are satisfied. So this is our solution. X1 and x2 is 0.4 and 0.2, and corresponding value should be f solve. So this is corresponding value of 0.5. If you want to check other values also, you can do 1, 2 and try to see. This is 100, 1, 1, 0. Okay. For 1, 1 we are getting the value of 0. Then it should actually give us that value. It's providing us the value of 0.5. Yeah, but we cannot use 1, 1, sorry, again. Yeah, so I'm just looking at one part only, but this solution is subject to all the constraints also, right? So I have to look at the constraints also, that these things are also satisfied. So the function value is minimum following this constraint at this particular points only. The points are 0.4 and 0.2, where your function value is 0.5, 0.52, right? Obviously 1, 1 it gives the value 0, but then your x1 and x2 cannot be greater than 0.4, right? It should be within the 0.0 and 0.4 that has been provided. So this is how you can solve the constraint problem. Then next again we have some optimization problem. This time we haven't been provided, you have to what function to use. We have to use a suitable function where you have this objective function subjected to some constraints. So I see two inequality constraints and bounds on my solutions, right? So here take the initial guess as the midpoint of the bounds and give your answer up to the one figure after the decimal point. So let's try it and solve this. I think we can use this. Problem 5. My function becomes x1 minus 1.5 square x2 minus 0.4 square. So this is a equation of a circle. Initial guess, we have been asked consider a midpoint. So 0 and 4 midpoint, let's consider it as 2, 2, 2, comma 2. Now we have to write the constraints. So since we don't have any equality constraint, I can put A is equal to null matrix. B can also go as a null matrix. So you can create them separately, or when you are calling the f mean conf function, instead of writing A and B, you can just write the null matrices here. For the equality constraint, now I have two equations. Okay, so one is now again, sorry. So for the equality constraint, I have one linear constraint and one non-linear constraint. So what we learned in the help command, that when we have a non-linear function, we have to create a separate function for that also. So we will do that. Before that, let's provide the inequality constraint data. Okay, -2 and 1. Again, sorry, this will be empty. A and B eq. We have inequality constraint given. My mistake. -2 and 1. -2 comma 1. Corresponding value is -1. Yes. A equality constraint, B equality constraint are 0. Now for the bound part, here we don't know. We have only bound on one variable, right? Not on the other variable. So in that case, what to do? Can you think about it? So here we have bound on only one part and not on the other. So in that case, what I can do? Again, let me go to help of f mean con part. So for the inequality constraint, I have to use not inequality. For the non-linear constraint, I have to create a separate function. We will create it. That function will provide us two values, C and inequality and C equality constraint data, right? So this will be less or equal to 0 and this will be equal to 0. This we have to provide it in this fashion. Okay, now bounds. So bounds on x and y, we have to provide it at both values, right? Now I don't know the value of I don't have bounds on both end for x1 and x2. Rather, I have bound on one end for x1, bound on other end for x2. So in that case, what to do? Can you think something about this? I have one idea that, but before we move forward, maybe you can think about it. First, I will write the non-linear constraint function, and then after that I will give you what we can do about this when we have only one directional bound. There are some examples also given. This is how I will provide the function data. So let's see. we will create function which provides C and CEQ is equal to non-linear constraint of X. Then here I have non-linear inequality constraint, so my C is equal to 4.5 times x1 square, sorry 4 times x1 plus x2 square minus 11. So this is my C. Oh, minus 18 again, my mistake, minus 18 and CEQ. So since I don't have any non-linear equality constraint, I can do the CEQ. Okay. Now coming to the bound part, right? See, in the help manual also, when you will see the bound values are on both ends, right? So if you don't have the both hand data, this itself, this bound itself is nothing but an inequality constraint. If you will see, it's a constraint. I can consider this as an linear equality constraint which says that x2 should be less or equal to 4. I can consider this as again a linear equality constraint. Here it says that x1 should be greater or equal to 0. So I can write it minus x1 will be less or equal to 0, right? Then you can put it into your non-linear equality constraint part. So first condition on x1 which says minus of x1, I don't have any x2 value, corresponding to that this is 0, right? Then second linear inequality constraint says that x2 should be less or equal to 4. So this here coefficient will be 1. This should be less or equal to 4, right? We don't have equality constraint, then I don't have to worry about bounds anymore, right? So this will take care of the bounds which says that minus x1 is less or equal to 0, which says this condition. Second part says that x2 is less or equal to 4, which satisfy my second bound, right? Now we can find the solution using f mean con. I have function value, we have x0 value, right? We have a value, b value, a equality value, then you have b equality value. Now for the lower and upper bound, since we don't have any lower and upper bound, you can keep them blank here, like the case they have shown it here. We can keep them blank. So let's say LB is equal to blank, UB is equal to blank. So this is LB, this is UB, and now my function which is non-linear constraint part. Okay, let's see how it works. Invalid expression, line 51, column 11. Oh yeah, here. Okay, now let's see. since I'm providing function within this cell, it should be at the end of a script, right? So here, and then now I think it should, yes, it has given the answer for this function. If I start with the x0 as 2 2, my optimum value are 2 and 3, x1 and x2 optimum value are 2 and 3. Let's see whether they satisfy this condition or not. x1 is greater than 0, yes. 2 is greater than 0, 3 is less or equal to 4, that is fine. Here minus 2 times 2 minus 4 plus 3, which is equal to minus 1, is equal to minus 1, right? Then this condition. So if you put 4.5 times x1 plus 9 minus 18, which will come to equality constraint. So actually your solution is lying at the boundary here, like both the constraints are satisfied as a equality value, right? So your solution is lying at the boundary, and corresponding function value will be 1.25. If you want, you can check the other values also. Let's say 2.1 and 2.9, something. It's higher, right? Obviously you have to check the whether the other constraints are met or not. I'm just checking it randomly, right? One another way to visualize this will be to look at the plot of your function, the way your function looks like, right? So here you have this equation with you, right? So we previously learned about the EZ plot, right, where you can use the functional form like this to plot your plot your data, right? So let's say if I try to visualize this EZ plot, I have x minus 1.5 square plus, let me call it y minus 4 square error in inline expression. What happened? Function x by k. x1 x2. Just a minute. Oh, additional parentness also. It's not coming is equal to 0. Just it's like L is that what? to provide the domain part here. X min, Y min. Minus 555. Okay. This plot is not working for some reason. EZ plot. Anyway, I'm not sure why this error is happening. So basically I'm what saying is that you have to visualize this problem. So what this problem says that you have this equation. So this is nothing but a equation of circle, right, with a center as 1.5 and 4, right? Then you have two constraints, like four inequality constraints. So if you will put this, so this will represent line, this will represent line, this is representing line, and this is some parabolic part, right? So if you will see, the intersect of all this part will give you the region in which your solution will lie, out of which your function value will be minimum at the boundary which at the point which satisfies all of this constraint, right? So mostly this will lie on this intersect point only, since it's a circle, and that intersect point will lie on this boundary. That's why it's equality constraint. The solution is at the edge of this part only, right? Because your function is a circle, right? So you all what you can do is you can visualize this also. I think I'm making some mistake in the EZ plot part, but do the EZ plot to see the circle, add this inequality constraint to the EZ plot, and then see, then you will be able to understand the region for which you are getting the solution, right? Now next you have similar two problems. Here the problems is just given in the different format. They are in the descriptive part. You have to create the function form on your own, right? So first is finding the one is that you have given the right circular cone is to design with a minimum possible surface area. Cone volume has been given, so it's a fixed value, so some equality constraint. Maximum base radius is given, maximum height is given, so there is constraint on radius and height. Initial guess value is provided. Use f mean constraint function to find the minimum value of the surface area, right? So you have to create a function here on your own. Similarly, you have the second problem where you have to find the heat exchanger, minimum cost for your heat exchanger, right? So what should be the radius of your heat exchanger for the minimum cost? Now since we are out of time, what I will do, I will stop it here today. If you guys want to try it out, you can try it out this two problem on your own, or else from the next class we will start with this two problem. to this two optimization problem, and depending upon the content we might solve some of the optimization problems in the next class, or we will move forward with the next data fitting part. Okay, so I will stop here. Thank you for joining.